If everybody's back, then maybe I can address another part, going back to the observations that we're having. So talk a little bit more about the errors that are involved. So this concept of coherence is an important one, and let's discuss that. So basically, you need to imagine what happens if an electromagnetic wave comes from the sensor, travels through space, through the atmosphere, and then it hits the Earth. Then basically there will be lots of interaction. There will be signal that goes through the Earth. So if we have dry soil or dry snow, it will go through. There will be dissipation. But basically, all the atoms which are kind of activated over here will cause new atoms on the interface, and it comes back. So basically, that way we get a reflection that we can observe. Now, if the surface is very smooth, and smooth is in the wavelength of the radar, then we get specular reflection. So it moves like this, and we get not so much back. So the SAR image will be dark or black. If it is rough terrain, then we get reflections in all kinds of directions. So we get more reflections back. And that means that if we go from specular reflection to more, let's say, rough reflection over here, and you could imagine that if this area is also tilted, then you also will get more reflection back. So this amount of reflection matters. And so now we need to make a statement on the quality of the observations. Now, I showed you this picture before, and I showed you actually this equation. And that was not completely correct. And the reason for that is that there's also some interaction that happens when the satellite signal hits the Earth. And I included that here by hand, identified as the scattering phase, right? So if, again, this example where we take the roof of this classroom, the one part of the phase that the satellite measures is dependent on the distance. The satellite is 1 centimeter further away from this pixel, it will change the phase. But the other part is the random phase, which is due to the coincidental position of all the points in the pixel. So I have that at time t1, and then I also have that at time t2, right? Where I measure the pixel. It has maybe there's subsidence, this has going down. But there is also at that time there is a scattering phase. Now, one thing I could do is what I do actually is take the difference between the two. I subtract them from each other, and what is below is then the difference between the two phases, which is the difference between the distances, but also, of course, the difference between the scattering phases. Right? Now, in response to your question, what we said is, so suppose that nobody moves and the scattering phase stays the same. If that would be the case, then this one minus this one is 0, and the whole thing is irrelevant to me. Right? But obviously, if the scattering phase changes, so if we all start to move and we move the monitors, and then the satellite will see something completely different. I also have been talking with some of you about the effect of snow, for example, in winter. Right? So we get reflections now, and then all of a sudden, maybe there's 1 meter of snow. Then the scattering phase is different. The distances they're still there, but it is kind of obscured by the change in the scattering phase. Now, if the scattering phase is completely different, then we use the term coherence, a value between 0 and 1. That would be 0. There is no correlation between the images in that case. If it is perfect, so like a corner reflector, which nothing changes around it, then it's 1. And of course, we have this whole range in between. So this coherence indicator is a metric that we use to get a bit of feeling of how good our measurements are. Okay, so it's a metric of how much two SAR images look alike. There should be a W there. It's an indicator of phase quality, and this is the definition of it. So this is a gamma. We use the gamma for the coherence. And what you see here is the complex multiplication of the two pixels, the two acquisitions. So one complex number times the complex conjugate of the other number. So we'll not go too much into complex statistics, but the E that is standing in front of that indicates the expectation operator, a mathematical operator. Now, what is the expectation from a single measurement, we don't know, right? So if I measure the length of the table and I measure 2 meter 50, then I just have the number 2 meter 50. I cannot come up with an expectation, or I have no clue on how to make this any better. The way that we do it in practice, if we, oh sorry, this is a bit messed up, is that we don't use the expectation, but we use the summation operator over here. So if I want to know the length of the table, and I measure it 100 times, and I do take the sum of all these 100 times and divide it by 100, then I get the average, right? And the average is the realization of the expectation, if you follow me, right? So the expectation is just a mathematical quantity, which I know, or maybe I don't know. It's just I define it. The average is something that I can really do with numbers. So basically what you see here, let's go back to this one, because there's just the expectation. If we replace this by a summation, so if we average stuff together, then we can get an estimate for that coherence. Now, when we were working to lunch with some of you, I discussed about my favorite example is the house in the potato field, right? So suppose that you have a big potato field of 1 by 1 kilometer, and you would like to determine the coherence. So of 1 pixel in the middle of that potato field. So what you could do then, if you just look at that single pixel, and if I would read out that number and I put it in an email, send it to you, then you have no clue what the quality is, right? If we now would assume that we take an area of maybe 10 by 10 pixels around that center pixel, and if I assume that all these pixels have the same characteristics, then I can make an average, and then I can get an expectation, I can get a quality metric, right? But that then only holds under the assumption that all the 100 points, 10 by 10 pixels, all the 100 points that I use are stemming from the same statistical distribution. They are all potato field, right? Now, if it's a potato field, that's a fair assumption, right? And then I can do that. So I take the average spatially to tell me something about the quality of that particular single pixel in the middle. However, suppose that I now have a house inside the potato field. So I have a huge potato field, there's one house in the middle, and I want to know the quality of that house. Then I can go there and I can do the same trick. I took a window around it of 10 by 10 pixels, and I average all these points together. But only the center pixel is the house, and the other ones are all potato field, right? So then that assumption doesn't hold. So I can do it, and I will get a number. Probably the number will be quite low, but the reflection from that house is probably a very good one. Right? So the point that I'm trying to make is that coherence is something that we need to calculate. And in order to calculate it, since we don't have any redundancy, we only have one measurement for one moment in time, we cannot average, only if we make assumptions. And you need to keep that in mind. So for example, in the portal that you may be looking at, there is this number, if you click on a point, there is a quality. It says quality is a number between 0 and 1. And that quality is somehow related to this coherence level. If the quality is 1, it's typically a good point. However, also there, we need to make assumptions on how to compute that quality. So for example, if I have, let me draw that. If I have a point which has a strange behavior over time, so maybe, so let's take a point here. So this is time, and here, if the point is moving points all over this, all right, and then I compute the line, I can look at all the differences between the measurements and the line, and I can use that to make a quality estimate. And then, of course, if my points are much more further away, I have a poorer quality. The quality number will be lower. However, if I have a same situation where, let's say, the points are doing this, so they're actually very good, and all of a sudden they're going to do this. And if I now fit a straight line through this, I'm going to get very big residues. So the difference between my model and my observations is very big. So actually the quality will be very low. The number that you will see there is very low. And this is simply due to the fact that my assumption in computing that quality was that I need to make a fit to a predefined model. So point that I'm trying to make here is that so we can use these quality metrics, but you always need to understand how they are computed, right? If they are computed in a way that is for your particular application, so we were just looking at a bridge, for example, where there was thermal expansion, so maybe the points do something like this. right? If I would now fit a straight line, then this point would have a very low quality because the residues with my model are big. But if I would choose a different model, if I would choose the sinusoidal model, then the differences are much smaller and my quality would be higher, right? So this is simply a matter of how I compute that quality. Okay, so that is coherence. Let me see here. So the implicit assumption here is that I can use averaging in order to compute it. Okay, so a couple of examples. So this, for example, a DEM from Tandem X, so the German satellite. So this is a nice picture. Here we're going to see the amplitude. So this is an ice area with there are some land. This is ice surface. So you see in the amplitude, strong reflections from the land, less reflections from the ice. If we now look at the coherence, we get this. All right, so now actually 0, or let's say 1, so white means very high coherence, very comparable. So the rocks here are very comparable in these images. And the ice also quite comparable. There are some areas which are black. These are probably holes in the ice where we see the water, and the water changes over time. If we look at the face here, we see a beautiful face with fringes here due to topography. And this is the ice, it's quite flat. There are some fringes due to motion of ice. But this is so where the coherence is high, here, so where it's very high, there I have a good phase. So if you look at this little dot over here, see, so now here, that little, where it was black, it's now very noisy. So the quality there is lower. So I can use that coherence, and I will not go into the details, but if I have that coherence here, the gamma, I can compute the standard deviation of my phase. And that is then what I need to get a precision estimate of my scatterer. Okay, let's go over this here. So I can do all the things, go to the probability density function. I can average points together. So we call that multi-looking. So 1 look, 10 look, 20 looks, and you see that these probability density functions get smaller, so I get better phase quality. So I can do all these kind of things if I have the coherence. I will not go over the equations here. You can look at that a little bit later. Now, there are 3 slides that I want to use to show how does coherence decrease. So, like I said, coherence is a metric for how two pixels, the same pixel, look alike. And it's dependent on the temporal coherence. So that is how did things change in time. So if I have an agricultural field and the farmer plows its field, then the temporal coherence will go down. Then I have the geometric component. How far are the satellites apart? We discussed that before the lunch. If the satellites are very far apart, they are not so comparable anymore. This is volume scattering relation. This is the Doppler, the viewing geometry. Then we have all kinds of noise that we introduce in the data processing. There are ambiguities, and there is the signal-to-noise ratio of the instrument itself. So basically, the message is that the coherence that we get in the end is the sum of a lot of components. And actually, this thing here, the temporal component, this is very important because this depends on the area that we're looking at. If it's a forest, then the decrease here will be very strong. So it will influence the total number significantly. So if we have motion, temporal coherence, so temporal decorrelation, so if all these points within a pixel change in position, and we have 100 acquisitions here, then all the values will vary randomly between -π and +π. And it will not be able to draw a nice line here because it's basically complete noise. Okay, these are just a couple of text slides. I'll skip them. So another important thing to remember is that if we choose longer wavelength, we are less sensitive to temporal decorrelation. So for example, if we're using shorter wavelength, like X-band, the wavelength is so short it cannot go through the trees, and it will see the top of the trees, the canopy. And it is very sensitive to changes. If we go to longer wavelengths, so C-band or L-band, so basically we can see through the trees and we see what is below. P-band is even better in that sense. Okay, this is what I already indicated. So if the satellites are far apart, that introduces noise. And here are a couple of examples for the same area. So this is a one-day interval between the two images. This is an area in the Netherlands, so this is the sea. Very nice, colorful face, beautiful. If we go to 1 year, we lose information. 2 years, 3 years, 6 years, it becomes very, very noisy, right? Now, the thing that I would like to continue with after the next break is the time series. So if we see this image with one image, two images with a 6-year interval, we could conclude, okay, there's completely noise, it's not useful. But in fact, there are hundreds of thousands, probably millions points in here which are good. Reflections from houses or from objects or from the streets. The picture of Riga that is in front of you now, if we would just take an image with 3-year interval before and after, it would look more or less the same. Right? But the algorithms that we're using in the time series allow us to find those good points in these images that are useful. Okay, so let me then go to the next part. That is the atmosphere. This is also an important thing to get a feel for. The area that you see here is an area which is about 100 by 100 kilometers, and it's always the same area. The color bar changes quite a bit. So for example, here we have a color bar that goes from -4 centimeters to +4 centimeters. So red here is about 8 centimeters different from blue. Now, the time interval between these two images is 1 day. So it cannot be that there is 8 centimeters of deformation or subsidence just in 1 day. So basically what we're looking here at is the turbulent atmosphere. In this case, there were thunderstorms on both days, and you have this is like a thunderstorm. And what happens in a thunderstorm or in a big cloud is that in such a big towering cloud, it consists of droplets, right? The droplets are not so much of a problem. We can see through the droplets, but in between the droplets, there's water vapor. And that water vapor in a cloud is 100% or maybe even a little bit more. So the relative humidity is very high, right? So I'm talking about the gas that is in between the droplets of the cloud. Now, if I have such a cloud system, let's say over here, suppose this is a very big cumulonimbus cloud, or so I look with the satellite, then I go through this cloud with all the high water vapor, and then I come out here and touch the ground, and I go back through the cloud. So in that whole area, I get a very strong delay, and that delay can be up to several centimeters, maybe a decimeter even. Now, next to the cloud, what is happening? If you have a thunderstorm, if you're in the meteorological field, so there's convection. So in the cloud, there is air going up. That is where it cools off and it releases moisture, and this is where the energy is transported in a thunderstorm, for example. But then it cools down, and then at the side of the cloud, it goes down. Right? So basically, in the cloud system, you have this pattern of upward rising air, which is below here, very warm and very wet. It goes up where it dries out and gets colder. And if it's cold, then here it is colder than the surrounding and it drops down. We call this also subsidence in meteorology. So a ray from the satellite goes here through, it has a large delay, but the ray next to the cloud has a very low delay. Right? So differencing between this point and this point is huge, right? 8 centimeters of difference. Now, you can also look at, okay, so this is an extreme case. What do we normally see? So here the error bars or the color bars are between -1 centimeter to +1 centimeter. And basically the message here is that every combination, every time, the atmosphere is completely different, right? And this is what we know, right? If you look at out of the window, you will see that cloud patterns are different. But even if there are no clouds, the water vapor distribution, what you see over here, is constantly different. So that's a big problem, right? If we would only have these images to make the product of Riga, you would see that maybe the city center would be subsiding 8 centimeters relative to the surroundings, right? So it's a huge error, and we need to get rid of it. And so this is also where all the conventional INSAR techniques stopped at some point, because actually there's no good way to estimate this signal. not with atmospheric models, not with GPS, not with meteorological satellites. It's simply too strong. The meteorological data are not good enough to capture this. So the trick, I can already tell you how we solved it. And the trick is that we don't use only 2 images, but in this case we use 133, right, for your data. So in these 133 there will be several which will have a strong atmosphere, but actually we can, in our data processing, we do estimate it actually. So we get what we call an atmospheric phase screen, so we have a bit of an idea of how it behaves. We estimate that, we get rid of it, and then there is still some remaining stuff, but the remaining stuff can be averaged out, right? So it could be that one single image, one single point on which you click has one single epoch in time where there is an offset simply because it was very, very bad weather. But overall, it should not affect the results too much. Now, this is also one other reason why we used 133 images, right? Because if we would use only, let's say, 10 images, and one of those 10 images would be like this, then it would dramatically change our results. You can also see that a little bit if you use your time slider in your portal, and it starts with going from the beginning to the end of the time period. If you narrow that down to maybe a month or so, so then basically you're only looking at variations over a short time interval, it will look very, very noisy. You will see kind of patterns and bubbles and everywhere, and that is partly, there are different reasons, but partly that is also because this atmosphere stuff is then still so much in there. Right, so you should be careful not to choose the time interval too small, because there can still be artifacts there. So again, the basic message is the atmosphere in this case is our enemy. We need to be able to solve for that. Okay, yeah. So I'll skip through this. You can do many different things. So what we're doing now, for example, with the Royal Met Office, is that we're using these data for the weather forecast. Right? So you can actually, this is the best water vapor measurement that you could have. And if you know that there's no deformation, if you know the topography, you can get a very good estimate of water vapor, much better than GPS could give you, and way better than meteorological satellites with radiometers can give you. Okay, so then that was talking about the observations, right? So I talked about the precision with the coherence. Before the lunch break, I showed you the signal to clutter ratio. So we know now something about the observations and how good they are. Now we need to relate it to these unknowns, right? So we have 2 unknowns, displacement and height. So in linear algebra, we call that a rank deficiency, right? 2 observations, 1 unknown, 1 observation, 2 unknowns. So we cannot solve that. So what we usually do, opportunistically, we use a DEM and we subtract that. That is what we call the functional model, which relates the unknowns to the observations. Then we have the stochastic model, and the stochastic model describes the quality of the observations. So it's a big matrix, and we can include all these information about the coherence and about the thermal noise and all these things in there. Okay, so I'll try to make this short, but basically this is the ideal situation. Actually, it is more complex, because one thing is that we have these ambiguities over there. So basically, if we look at this equation, there's also an integer number that times the full cycles that we need to estimate for every point. And this is a big disturbance, right? Because this thing is unknown for each point and for each epoch, unless I make assumptions, right? So if I sometimes I say in courses like this that I start my presentation by saying that INSAR doesn't work, right? And it's true. So INSAR doesn't work, right? And why doesn't it work? It's because that every observation, if I measure an angle of 10 degrees, it could also be 360 degrees, or it could be 730 degrees, or minus 350 degrees, right? So all these options are possible. It's infinite, right? So this is why, in principle, INSAR doesn't work. How come that you can still get something useful out of it? Well, that's because you make assumptions, right? So you assume that it is not so likely that a point which is here relative to a point which is 10 meters further over the time interval of 6 days will move more than 3 centimeters, right? Under those kind of assumptions, then it works, because you exclude all these other options in the solution space. But it's very important to start with that perspective. We cannot do magic, right? So in principle, we have a problem that is unsolvable, because we have, even if you assume that we have the elevation, we still don't have the displacement, and we don't have the integer ambiguity. Okay, then we have all these other things. So we estimate the atmosphere, the orbit errors. I think I have a picture of the orbit errors also. Let's see. This I already discussed. This one is also already in. Okay. No, this is not in here. Okay, so this is the, let's stop here. So the most important part of this part of my presentation was, okay, so we have the observations. There is a quality involved that is largely dependent on the temporal correlation. So how much does the pixel look alike in an image that we acquire now and an image that we acquire 10 days or 12 days later? Questions about this? No? Okay, so if it's okay, I would like to say something about the displacement vector. Also a question that came by. And yeah, I have a couple of slides on that, just to interpret, to help the interpretation. So if we have, if something on the Earth moves, we can express that with a displacement vector. So you also, I think one of the questions that I put in the Google sheet was, so why are we talking about displacements rather than deformation? And that is mainly because a point cannot deform, right? What we're looking at is all set of points, like a point cloud. And a point can translate, it can move in a certain direction, but a point cannot deform, right? Only if we have 2 points on the same building or so, then the difference between those 2 points, that will relate to deformation. So here we're always talking about the displacement vector. So one point moves in between the different consecutive images. Now, whatever that motion is, so we can express that in, for example, this coordinate frame, east, north, up. Right? That's a Cartesian coordinate frame. So we say that a point has moved 2 centimeters to the east and 3 centimeters to the north and 5 centimeters up. Right? And that is the unknown vector that actually I would like to get. But the whole viewing geometry is such that of those 3 unknown parameters, I only get one observation. Right? So this is the same kind of problem that I was just discussing. It is a rank deficient problem, and we cannot. So we cannot estimate these 3 components from one observation. So that's basically the main message. So everything what you see over here in the image or in your portal, it's also one of the questions, is in the line of sight. So these are line of sight motions. Now, of course, if you have any kind of clue of what is going on, you are free to make your own assumptions. So if you say, well, I know that I've been extracting water here and I'm in the middle of that bowl, so I simply assume that I'm only have a vertical component, then you're free to project that line of sight component to the up component only. You say, okay, these 2 are 0. I know that for some reason, and then I get this. But this is purely dependent on your knowledge of the problem. So if you look at this viewing geometry, and here in this slide it is for the Netherlands, but basically we have this descending orbit flying over here and ascending orbit flying over here, looking from 2 angles. So the viewing geometry is like this. Now, there are different coordinates that we need here. One is what we call the 0 Doppler plane. That is the red plane that is kind of orthogonal to the orbit of the satellite. So if the satellite is flying over here, I have a plane which is orthogonal to that, perpendicular through that, and ideally my satellite observes in that plane. Now, if you have that plane in the 3-dimensional world, it will kind of cross here with the Earth. So that is the 0 Doppler plane. The second thing is the incidence angle. Right? So if I have, if I look at a point which is close by, I have a very small incidence angle. If I go further away, this incidence angle will get bigger. So the viewing geometry depends on where I am in my image. So in the Riga portal, it's an ascending image. So a point on in the west of Riga has a much smaller incidence angle than a point on the right of Riga. You can check that if you click on a point and you look at the information, it will also give you the incidence angle. Maybe I should do that. That's a good demonstration. Okay, so I'm going to zoom into a point here on the west end of Riga. Okay, so for example, this point over here. Why doesn't it pop up? Reload. Okay, don't know why that failed. So what you see here is this particular point and how it behaves over time. It has a point ID with an L stands for lines, a P stands for pixels. So we have a matrix where every element in the matrix has a number so that we can talk about it. And it has a linear displacement rate estimated here from these data. It has a quality that we just discussed. It has a point height and a DEM height, and there were 133 observations. Point height and DEM height I'll discuss in a minute, but basically there is much more of this point, and then you can see that if you click on this properties button over here. So the most important things are, again, but now you see the latitude and the longitude of that particular point, so you can put it on Google Earth or in your GIS. There's a line and a pixel value as 2904 and 19071, that's over here. Point height, DEM height, I can talk about that in a minute. There's a geoid elevation, and there's the incidence angle. So here we have 35.9 degrees, that is the incidence angle for this point. So 35.9. Let's see if we now zoom out and go to a point in the other side. So it's probably not that big of a difference because it's a small region. But let's have a look at this point. Here the incidence angle is 36.8, right? So there's 1 degree of difference in this point. So depending on where we are in the image, we have a different incidence angle, and we need to take that into account. Okay, so we have these two coordinates. Now another thing that you need to imagine, so a lot of people, if you're using this, they are computing with the heading angle of the satellite to compute this angle over here. And that is actually wrong, because the satellite has an angle which is defined over here, but it is looking at a point which is more to the north. Because of this, it's not going completely north-south. And the meridians of the Earth converge. So actually, if you look at the angle of this plane, so if you're going from this distance to this distance, the azimuth of that angle changes. So that is an important thing to remember. So this is the zero Doppler plane. Let's skip this over here. So if we have one satellite observation, then basically we have something which we call the null space. So there is, this is one dimension. There's a three-dimensional space of my solution space. So if this target moves with the red vector over here, so let's do this with my arm again. So if the let's say if this is the vector, the displacement vector, I'm measuring only line of sight motion, so in this direction. So every point which is in this plane orthogonal to it, any displacement in this direction will not be visible in the satellite. And that is the null space or the null plane, as we call it over here. Okay, now what happens if you have now two satellites or more? If you have, let's say, 3 satellites from different viewing geometries, or M satellites and looking at the same area, then things work out, because then you can make this computation. You have 3 unknowns, several observations, then you can compute this, right? So that's great. So what do we need? We need to have the same point on the ground. We call that a RUM, so a region of uniform motion. So basically what we need to do, as I told you, from the ascending satellite we're looking from that to that side of the building, from the descending satellite we're looking at that side of the building. Maybe those two are different, because the street there is moving at a different rate than the street here. Then I cannot push them together. But if I'm interested in a gas field, for example, where I have smooth motion over a subsidence area, it's okay if I have a 100 by 100 meter region and I average all these things in this region, right? Or if I have a landslide on a mountain slope, it's okay if I take a certain area on that slide and assume that that moves as a whole. So this is what we call the RUM, the region of uniform motion. Now, if we have that from different angles, then we could, in principle, mathematically, we could solve this. Now, the problem is that there are different satellites looking at Riga, but they are all in these polar orbits, so they all are looking almost from the same direction, right? So we don't have the nice thing that we look from 3 different angles to the same object, because then we could solve this. So basically, we are much less sensitive in one direction than in the other. And that is what we call the null line. So there are these conditions, so we need to have at least 3 observations, because we have 3 unknowns. We need to have a region of uniform motion that needs to be defined, and we need to have a full rank system, basically, that we're looking that the rows of this matrix are completely different. So in principle, what we typically have is 2 observations. And actually, Wietske, my PhD student, she made this little viewing geometry for Riga, this notebook. I think it's also, you can link it and download it. So what she did yesterday is she did computed the viewing geometry for the satellites here. These are the coordinates. And there are 2 ascending and 2 descending images available, she says. So here are these 2. So you see, for this particular coordinate, these are the incidence angles from the different satellites, and this is the azimuth of the 0 Doppler plane. And maybe I should explain this too. So if we have, if you design a satellite and you want to cover the Earth, and if this is the size of an image, and this is the equator, then on the equator you would like to have the images next to each other, right? Because then you cover the entire Earth. You don't want holes in between, because then there's an area that you don't see. So you put them over here. This is the equator. If we now go to the poles, the meridians go together. So this points to these images which are next to each other on the equator actually collide if we go to the poles, right? And here we are at 56-degree latitude. So actually here we have more than 50% of overlap. So that means that for every square meter in Latvia, we'll have 2 ascending and 2 descending images, simply because these images overlap with each other due to the latitude that you're on. So this is the reason that basically you can get 4 images. So what does that mean for you? So if you have Sentinel-1A operational, 1B doesn't work, but well, let's make the calculation for the Sentinel-1A and 1B. So 12-day orbit. So this one is every 12 days, this one is every 12 days, this one is every 12 days, this one is every 12 days. So 4 images in 12 days. So that is every 3 days, right? Then we have 1A and 1B. That is 1.5 days. So basically every 1.5 days on the average you have an acquisition over Riga, right? So for those of you who are interested in asset monitoring, basically you can have an observation typically every day, more or less. So that gives you very high sensitivity to monitoring, like the bridges that we've been talking about. Okay, then what we can now compute is what we call the null line. That is this thing over here. So for 2 geometries, we have the null space of one image. This is descending, and the blue one is the ascending. And if I rotate this, you can appreciate this a little bit, I think. Right, so if we have 2 planes which are crossing each other. I think I'm moving it too fast now, but northeast up. So the intersection between the 2, that is the null line. Let's look at it like this. So 2 planes which are crossing each other means that there is a line in which they are crossing. That is now, for 2 images, is our line in which we're insensitive to motion. I explained to you, if you have only 1 image, 1 viewing geometry, we have this line of sight and we have this plane, so we can be anywhere on the plane, we don't know. If you have 2 lines, two images, then the solution space reduces to this red line, which we call the null line. In that line, we're not sensitive. Okay, what is the consequence of that? Let's go back to the image. So here you see that null line. So the null line, we can define that for every location where we are on Earth. So also for Riga, we know, okay, this is the azimuth and the elevation of the null line over here. So what we could do now is, well, there's several options. So one option, maybe three options that I should discuss. We only have two observations, three unknowns. Option one is that I'm going to show you an east component, a north component, and an up component. That is what a lot of people do. If you look at also at the Copernicus surface, so they have an up component and an east component. But actually, since this null line is not horizontal, but it's tilted, these two numbers are correlated. So you get big errors, depending on where you are, but you can get very huge errors. So simply showing the vertical and the east component is, in my opinion, the worst thing you can do, because you're going to really, you know that you're going to give wrong results. The second option is what we call the strap-down approach. So basically, we define a new coordinate system. This is east, north, up. But for an object like a bridge, we can compute the longitudinal direction. That is the direction in which the dike or the dam, some people were talking about dams, is going, or the railway. We have the transversal direction, which is orthogonal to that, and then we have the normal direction. So if you have, for example, a road or a railway which is going on the slope of a mountain, in this coordinate system I can now make assumptions, because, for example, many deformation phenomena are simply due to gravity, right? If you have a mountain slope, something is sliding down, we know that the gravity vector is the driving force. So in many cases, we can then kind of kick out the longitudinal component, because it is not the significant thing that we're interested in, right? So if we have a dike, for example, the Riga case, let's have an example again. I think there was this landfill that you noted me to. Where was that? Oh, here. Right, so here we have a landfill and a lot of deformation, right? Significant deformation with a kind of exponentially or polynomially decreasing rate. If we look at this from two angles, then it's perfectly fine to assume that the likelihood that there will be motion in this direction is very, very low, right? What would be the mechanism that there would be deformation in this direction? Likely is much higher that it's vertical and that it's orthogonal to that component, right? So if you define your coordinate system in a way that that is optimized for your particular asset, you can get very good estimates. The third option is, let me see, oh. This is this was the strap-down component. So if you have a landslide, for example, here the same thing. The transversal component and the normal component are important. The longitudinal component less. If you have subsidence, for example, it's the same thing. You can use this system. The other component, other option, is the null line aligned system. Again, so here we have the null line for a particular location. So the null line has an azimuth angle and an elevation angle. So what I can also do is simply choose a reference system that is aligned with this null line. So basically, it's a reference system that is orthogonal to this line. So in that plane, I only have two unknowns, and I can estimate them perfectly without a bias. So if I know the position of this line, I can still get two unknowns which make sense. Okay, so that is the thing that I wanted to show about the decomposition and the projection. Then maybe one other thing, you guys have been looking at these pictures, right? And one question that also came by is, what is the difference between the blue and the gray dots? Now in this case, this is the ambiguity level, right? Now why do we show this? So basically, if I zoom out a little bit, Right, so okay, we have a point over here. Maybe so the displacement here is minus 18. Let's maybe choose here along this line. So here the blue dot is approximately over here. This one is 28 millimeter up, and this is 28 millimeter down. That is the wavelength of the radar. Right, so if we look at this time series, then we can look at the quality. That gives us 0.87. That is pretty okay. But the most thing I learned from looking at the differences with the ambiguity levels, because if there's a big difference between these two, I trust my data. I will show you a trick in which we can look for, let's say, worse points. That is by, if we have this here, we can select here the point quality, right? And the point quality is a number that we introduce in principle when we start doing the processing, right? So here, if I go select the lower point quality, I get many more points, right? But these points will have a lower quality. So if I would go shift this down, I think there's probably somewhere a lower value. Okay, so now what you see is that this point quality, the value 0.42 and lower, that is what we see over here. And we have filtered out all the ones which are better. Now if we look at those points here and look at the noise level, okay, now you see that the difference between the values over here and the ambiguities, so the gray dots, is much less, right? So this is an area, a time frame, where I would not be very sure about the result. Now, obviously, if you look at a portal like this, you see dots, and there are also locations where you don't see any dots. So if we include all of them here, let's switch this all up. Okay, so there are many points now. You can see the orientation of the satellite orbit over here. But here, there are no dots, right? Now you could say, well, you know, that's bad, I have no information there. But basically, actually, I have information there. I know something because the radar has pixels over here, but the algorithm didn't pick them out. So that basically means that the changes in the land surface here are so big that something happened over here that the radar scattering was not comparable anymore. So that's very useful information, actually. So if they did something with the landfill in this period of, 2019 until now, I guess they did it here. They put new stuff over here, because here the surface of the Earth changed. That is information that I can get. Now, the other thing to realize is that if you process data, if you try to make a product, you need to make a decision here. And so, like I indicated, if you go lower than, let's say, 0.4, there's nothing there anymore, right? Now, does it mean that it doesn't exist? Well, yes, it does. It does exist, but we chose not to show it, right? And that is basically because if you go below that noise level, you're going to get lots of very, very noisy points. And again, if you are interested in a particular area, if you're interested in this landfill, for example, the best thing to do is to include those points, right? So you could simply show them. But if you don't know what you're looking for and what is the application of the data, you decide to keep them in. Okay, so that is the explanation about the relation to the noise. Then the last thing I would like to explain is the difference between PS and DS. And in order to do that, I have a little graph that I would like to show you. Let me see if I can find it quickly. This one here. Yep. So, well, this is a big graph, so let me first talk about it and then we'll discuss further. So, in the when INSAR was developed, so there was basically we used 2 images, and then people came up with the idea of using a whole time series of data. And so the first people who really came out with this, with a really landmark publication, was the group in Milano, the Politecnico di Milano, the group of Fabio Rocca, with Alessandro Ferretti and Claudio Prati. They were the ones who came up with the first idea of, hey, let's try to find a point which is coherent over a long time scale. And they called that permanent scatterers, PS. And permanent scatterers there became, let's say, the term that we use for those points which are permanently coherent. Now, then there was a bit of an issue because other groups also came up with the same kind of algorithms, and they would like to call it the same, but the university didn't want to use that name, so then it became persistent scatterers, because they could use the same acronym, PS, but they would not infringe the copyright and the patent things. But now, if we're looking at it, actually, I think it is a wrong choice, because so in that case, we had permanent scatterers, or persistent scatterers, and distributed scatterers. Let me first explain the concept. So, persistent scatterer in that philosophy is a point which is a point scatter, so of one very bright object, which has a coherent time history for the phase. A distributed scatterer is like a potato field, an area which has the same kind of roughness, or a grass field, for example, where there's not one dominant scatterer, but there are many little scatterers which all act together. Now, the term permanent or persistent means that such a point is coherent over the full time series. But as time goes by, you can imagine that many of those points occur, they are there at some point, but then they also are removed. So think, for example, of a house, right? A house is built at some point. So before it was built, there was maybe a bare field. Then all of a sudden there's a house, and maybe at some time later they take the house away, right? So if you look at the whole city of Riga, there are many areas, I'm pretty sure, where new houses have been built in the last 10 years, right? And we have data which go back to 1992, so that is, what is it? No, 30 years even, huh? So in that 30 years, it's impossible to think about points that are always there. And if you would only find a limited number of points. So in my view, this is the wrong terminology if you look at it. So I have a different way of looking at it, where we have PS and DS, but PS stands for point scatterers, and DS stands for distributed scatterers. So if you have the distributed scatterers, what can happen is that they are continuously coherent over the full time area series that you're looking at. It could also be that they're temporarily coherent, or it could be that they're incoherent. Okay, so this is water, for example. Water is a distributed scatterer. All the waves give you a bit of reflection, but it's incoherent over time. After a second, you lose it. If you have, let's say, a bare field, like a grass field, and it is a grass field for several years, then it may be coherent for a very long time. But at some point, maybe they will plant some crops there, right? Then it loses coherence. So then it is temporary coherent, only for a little bit. Or maybe it's only temporary, it's only coherent during summer. Maybe like here in Latvia, you have areas with a lot of snow cover. So it's coherent in the summer, but it's incoherent in the winter. That could be, right? Or other way around, if you have a crop, right? So a crop would be incoherent in the summer when the crop is high, but in the winter, the field is bare and it is coherent. So all these are examples of distributed scatterers which are temporally coherent. Now, obviously, if you go to the desert, for example, it could be that a point doesn't move like, you know, or is stable for a very long time. Or if you look at the surface of the moon, right? Continuously coherent, nothing changes, it's always the same. Now, the other thing is then point scatterers. Yeah, and you could have the same thing. So you could have point scatterers which are continuously coherent, so continuously coherent point scatterers. These are the class of points which over the full time series are coherent. A house that was there. You can have the same thing for temporary coherent. And here I put unlikely because it is very unlikely that you have a point scatterer which is incoherent. Usually point scatterers are coherent. They are there's a reason why there are point scatterers. Right, so this is the background of these buttons here. So what we can do, for example, if we click on the only, let's say, the DS, it's the PS over here, in this landfill region, you see that the algorithm here only defines a limited number of points which are classified as point scatterers. PS is point scatterers. So if you would simply do a point scatterers analysis, or PSI as we call it, persistent scatter interferometry, you would get these points. Of course, if you change parameters, you get more or less, but this is more or less what you get. Now this area, you would conclude, okay, this so apparently INSAR doesn't work here. Well, now if you do distributed scatterers, you find them, you get this here. Now what is the trick? The trick is that if you look at one pixel over here, it's a very bad pixel. But if we look at all the points around it, then all the points around it have a kind of the same behavior. So let's say the point is too noisy if we look at only at one point, but if we average points together, then it appears to be good. Now you can see that if we click on one of those points over here, okay, so this is a distributed scatter. There's another one. And if we click on this properties button, we see everything we know about this particular scatterer. So I hope you can read this. So it has a point ID, it has some kind of flags, a position, line pixel coordinates, point height, DM height, again I will talk about that in a minute, quality number, all the parameters that were estimated, so the linear rate, the quadratic term, the seasonal sine and cosine components. But this here is the important thing. So the number of DS neighbors here is 25. So what does that mean? It means that in computing this particular pixel, so this particular point that I just clicked on, we took 25 other points in the surroundings and we checked, okay, do they have the same statistical distribution? So we looked at the amplitude, at the phase, and we made a selection. Okay, so if these points are more or less similar, then it's okay to average them, right? If a point is not similar, we don't average. So in this case, that particular point is based on the 25 points in the surroundings. And then you have the problem of the houses in the potato field again, of course. So this, in some cases, this may be very valid, very useful. Some cases, it's more tricky. If we look at a point scatterer, here, like this. So actually see here a very interesting one. It has a very funny behavior. And here the number of DS neighbors is 1. It should actually be 0 if you, but it's just 1 point. It doesn't check with the surroundings. Yeah, so that is the explanation about the PS and the DS. Are there other questions about this part of the browser and the portal? Yes.
The browser, but about point scatterers and distributed scatterers. So essentially, that the point scatterers are, in a sense, more in general sense, more powerful, right? So they are better.
Yes, yeah, I would say so. They are better, but they also have a different interpretation, right? So it's something that you can more confine to a particular region, so or an object. Distributed scatter is also always a bit of an average of an area. So actually, this is pretty good for distributed scatter because this is all landfill. You can look at the picture here. I think it would make sense to do some kind of averaging, but DS, which are selected here by the algorithm, may not be so good because let's say if we have a DS over here and we look at points around it, then how can we say that these points around it have the same characteristics? So we do this comparison of the statistical distribution, so it makes some sense, but it's more tricky. It's more the interpretation is more difficult.
And another question about previously when we determined the displacements in 3 axes. So essentially, the idea how to learn the displacement or infer the displacement in different axes is to assume that in a single axis it won't move. It's very improbable that it won't move. So we just have the extra 2 axes where it will move.
Right.
So it's very pixel by interpretation, right? Very, very local, on local characteristics determine the interpretation.
Yeah.
It seems like
well, this is it's not completely true. Huh? So of these three options that I explained, maybe the most exotic one, because it's not so much used yet, is this null line aligned frame. Right? So if we know the position of the null line, and we do, then we know that our observations are not completely insensitive of all the displacements that are there. So if we estimate the other two components, they will be true, right, from a descending and ascending. So there is no bias involved, right? We also don't need to assume that there is no deformation in a particular direction. So it's not based on physics, it's simply the geometry. But we get the two components in a plane which is slightly tilted. For the other two options, you're right. So this is why I'm so against, let's say, this things that you see now on the European map, for example, because that is east and up. And that is very, very correlated, and there is no reason why north should be 0, right? So it is, you don't know, it's not shown, but it's very unlikely. But typically we have the problem that we only have 2 observations and 3 unknowns, right? So you have to do what makes most sense in particular cases. And for example, for a subsidence, where again the gas extraction or the gas production is one of the ideas here. So if you inject gas at a certain location on the ground, you're going to get this bulge that is going up, and usually that has a kind of more or less radial pattern, right? So the middle goes completely up, no horizontal motion. The sides, there is horizontal motion to the side. So once you know the shape of that bowl, it is, I think, very defendable to say, okay, that along those iso displacement lines there is no deformation, only orthogonal to it. So in principle, yes, you're right. It's a bit opportunistic, but in several application areas, it does really make sense, and I think it's defendable.
Yeah, I was more interested in how it seems like a very big hassle to interpret data this way, because you have to somehow model how it would move for every single pixel.
Yeah.
And this, I guess, this movement will change over time, possibly even. And
right.
Yeah,
that's true. Yeah.
It's a big undertaking.
Yeah. Other questions? No? Would you like to move on with a couple of the exercises? Is there another coffee break, Francesco?